Claro, mas vamos fazer uma rodada rápida de apresentações. Só dizendo o seu nome, que nível você está, nesse caso do professor, e a área da atuação genérica. Então, eu trabalho com ondas gravitacionais, começamos por aqui.
Seu nome? Seu nome?
Sim, já falei antes, Carlos Durante. Falei, não. Vai, Camila.
Camila Guitarres, eu sou pós-doc no INPE e eu trabalho em tecnologia e várias coisas dentro de tecnologia.
Você não é pós-doc?
Bom, por enquanto,
pelas próximas semanas. Ela é professora, pesquisadora.
Pesquisadora do INPE. Acabou de passar no concurso. Parabéns.
Você sabe. Quando cai de neurônio.
Sou a Natália, estou no último semestre do doutorado lá no Instituto de Física da USP com o Raul e trabalho com estudo em grande escala.
Eu sou o Rogério, eu sou professor do IF da Unesp, minha sala do lado do estudante. Trabalho também em grande escala e trabalho com grandes levantamentos de galáxias, IS e LSS.
Eu sou o Rodrigo, estou fazendo pós-doutorado em Donóstia, mas eu estou visitando aqui até dezembro. Eu trabalho também com estrutura em menor escala.
Meu nome é Matheus, eu acabei de entrar no mestrado essa semana, lá no IFUSP, com o Raul, e eu vou trabalhar com os dados do JPS, basicamente com a análise de espectro de potência e tal. Eu sou o Guilherme, eu acabei de entrar no mestrado também com o Rogério, lá no IFT, e eu vou começar o mestrado na cosmologia.
Eu sou o Tainá, eu estou na mesma situação que o Guilherme. Mesma coisa.
Rogério, orientador.
Bom, meu nome é André, estou no primeiro semestre do doutorado com o professor Sturani na área de gravitação lá no IFT.
Larissa Taqueira, eu estou aqui metade como organização do ICTP-SAIFR, metade porque eu acabei de terminar meu pós-doutorado em astrofísica estelar.
Eu sou a Maitá, sou uma aluna do mestrado, trabalho com ondas gravitacionais.
sou Liliane Nakazono, eu sou pós-doc no IF no grupo do Raul também, trabalhando no sistema de escala com dados de grandes levantamentos.
E será pesquisadora do OEM daqui a poucas semanas também.
Eu sou o Basta Riquelme, eu trabalho no Instituto de Grande Escala no ICTP, trabalho com o Rogério, NBS, NSC.
Eu sou Daniel, você meu doutorado com o Raul, estou trabalhando no Instituto de Grande Escala e aprendizagem machine learning. Como é isso em português?
Machine learning. Eu sou o Raul, sou professor do Instituto de Física, trabalho com cosmologia e estrutura em grandes escalas.
Beleza, e agora podemos oficialmente começar o segundo ano do Astro Cosmo Meeting, e a palestra é bem apropriada. Então, do Jorge, do IAG, nos falará do exoplanets. Então, estou muito ansioso de ouvir. Por favor.
Bom dia. Então, eu estava na gravação, uma coisa que eu estava pensando muito era...
Só dizer, todo mundo fala português.
You prefer English?
Não,
Okay. So, what?
Se nós dois somos os únicos que não falamos português, para mim é meio português, assim, dá para...
Pode ser.
You prefer in English? That's fine.
Você escolhe. Não todo mundo fala português.
Okay, so when I was an undergrad student in Peru, something that I liked very much was to go to the mountains nearby Lima, to clean the mountains and to look at the stars. And so at that time we made some philosophical questions. And I didn't know at the time that I could do some research that could be somehow related to those questions. So I have spent a lot of time in my research trying to find solar twins, stars very similar to the sun. So in order to do this, because I mean there are so many stars in the Milky Way, we try to select those with parameters very similar to the sun, meaning similar luminosities. That is the vertical scale, the absolute magnitude of the stars, and also similar temperatures, that is the horizontal axis. There is a third parameter that is very important, that is the chemical composition. So we try to select also stars with metallicity close to solar, so close to the metallicity of the sun. In this scale, this a log scale, that means that when it's identical to the sun, the iron abundance is 0 because it's the log of 1. So
can you explain the x-axis, the color index?
yes, the color index. So the color index is just a measurement of the flux in different filters. In this particular case, we have a spectrum on the top where we can see the filter profiles in the ultraviolet, U, B, blue, and V for visual. So from this filter, we can get, for example, the temperature. So this is why I said that in the horizontal axis, we have the temperature, because the color index is a measurement of the continuum emission in the stars. So we can sort of think of black body emission that have different characteristics, spectral energy distributions related to the temperature. So in the stars, it's sort of the same. So we can measure the flux, the continuum flux in some bands. In this particular case, we are using the band in the blue, B, and in the visual, the V, that is more or less the green. And then that is related to temperature. So in the case of the sun, the color index is, for example, 0.65. So the sun is more or less around here, in this point. Yes.
So if you're selecting by the color index and the absolute magnitude, I don't fully understand why there's the necessity of also imposing like the metallicity, because I was expecting that basically then you are in main sequence and you won't have any iron.
Yeah, good question. The thing is that the color is not so good because the color is there has some degeneracy between temperature and metallicity. This is because the stars are not black bodies. We have interaction of photons with atoms and molecules in the atmosphere. So we have absorption lines. You can see in the spectrum on the top, we have absorption lines. So the color doesn't depend only on temperature. It depends also on metallicity. So this is why it's important. We try to somehow try to guess which stars have metallicity close to solar.
So if you would to measure directly the temperature, you would just use that? It would be...
No, we also need the metallicity because it's because the stellar interior, the behavior of the star depends on metallicity. A star with different metallicity will have a different evolutionary path because the opacities in the stellar interior has some effect on the internal structure. On how is the internal energy transfer inside the star. So what part of the star is radiative, what part of the star is convective. So it has a direct impact on the star. So this is why we need, and also it's somehow related to stellar ages somehow, because if the star is very metal poor, then probably is very old. And also, if the star has almost no metals, if you don't have metals, then it will be hard to form planets. I will speak a bit more that later. So the horizontal axis could be also the classification of the star. The sun is a G2 star, and but we use mostly different color indices. Some color indices that do not depend much on temperature as much as the V minus V. I put here V minus V as an illustration, but actually we use several color indices. But the first 25 years of this search for stars like the sun was not successful. They were unable to find a star that is similar to the sun because there are just so many that it's very hard to say, okay, this is really close to the sun in physical parameters. It was a Brazilian astronomer, Gustavo Porto de Mello, who discovered that a star that is, you could say, okay, this star more or less is close enough to say that this star is a solar flame. And you can see the some parameters like the metallicity, the ion abundance is close to 0. The color that I just mentioned, V minus V, is also close to the sun. The sun is 0.65, so it's very similar. So this was the first time a star similar to the sun was discovered. Similar in physical parameters, in mass, and also in chemical composition, global chemical composition. So we started this project around 2005, and we have been observing with different telescopes around the world. So we take a very high resolution spectra with a resolving power of around 60,000, 100,000, or less. Try to characterize that.
What exactly is that image? The spectra are this way or that way?
Yeah, so this image is not real, but it is close to real because the way we observe, we do cross dispersal spectroscopy. So you have the telescope, you have at the focal point, you have to do a slit, a narrow slit, just to pass the starlight. Then the starlight will pass through spectrograph. Spectrograph is composed of a diffraction grating. Okay, this diffraction grating will cause the dispersion. You could also use a prism, but the dispersion is not high enough with a prism. Okay, so we use a diffraction grating. And the problem with if we work in low orders of the diffraction gratings, we have a problem. The problem is that the dispersion, if you want high dispersion, I am talking about, let's say, resolution of 10 to the 5, it means 100,000 resolving power, lambda over delta lambda. If you want a very high resolution, I mean, you have your CCD is just like this. Then the stellar spectrum is gonna fall just a bit on the CCD, just a very small part. Let's say 100 nanometers or so. So 100 nanometers is 10 nanometers. Okay, and so the rest of the spectrum will fall off the CCD. We will need a CCD detector, you know, like the 3
Size of this room.
You know, this. So we have a trick. The trick is to work in high orders using the so-called Echelle gratings. The Echelle gratings will work in very high orders. And the problem with high orders is that the dispersion angle is going to be superimposed. All the orders will be very close to each other. Like order 30 will be here, 31 will be just 1 millimeter away. So all the orders will be essentially superimposed. So the trick is that you have here the dispersion in the spectral direction. The trick is to put another grating, but rotated 90 degrees. So this is what we call cross dispersion. You rotate the other grating 90 degrees, and then the other grating will disperse the orders in the perpendicular direction. So this is more or less qualitatively, that is what we observe. So we do high resolution. So in each little strip, we observe like 100 Astro so, and we can cover the whole spectrum just with this trick.
So wavelength is increasing from right to left, down to up.
Yes, left to right is increasing, and then from bottom to top.
Yes, okay.
Here, for example, we have these lines here are very famous in not just in stellar, but also in stellar-electric astronomy. Those are from magnesium. Those are very famous in laboratory astrophysics, the sodium D lines. And this is H alpha, the very big line just behind the telescope is the H alpha. So the transition from the level 2 to 3, the hydrogen atom. So we have a tons of lines to observe, in the spectrum. All these observations are taken with the shared spectrum. So now we are very successful. People believe in us, but it was not that case at the beginning. The first time I brought a proposal when I was a postdoc at Caltech, I brought a proposal, and it was my near my worst rating. The grade that I got was near 0, I think. They thought that my proposal didn't make any sense. So I was a bit depressed at the time. And I said, okay, I wanna write another proposal, because in the committee at Caltech at that time, many people were from stellar-electric or cosmology. There were not many stellar people or people working on exoplanets at the time. And so I say, okay, I'm gonna write a proposal that is only interested for cosmology and so. So I wrote a proposal about Big Bang and primordial lithium abundance, because at that time there were some serious problems with the detection of the two isotopes of lithium, lithium-6 and lithium-7. And there were some, the thing is how you could make too much lithium during the first few minutes of after the Big Bang. And the other problem was how do you deplete, how do you make too much lithium-6 and how do you deplete lithium-7? So many particle physicists proposed some new particles. Many theoreticians proposed several models to try to fix this problem. So I used this opportunity to say, look, let's look at the star, let's do a better analysis. And so they give me a lot of observing. Yes.
So this problem of lithium abundance was like something measured, were like from directly from stars, from the composition of stars, or it was like
Yes. From the stellar spectrum, from very old stars, the first star that formed in the galaxy, we can see the absorption of lithium. Most of that lithium was formed at the Big Bang proximity.
So that was the result of the project. So there is no tension with Big Bang.
For lithium-6, no, there was no tension with Big Bang. We showed that the analysis that was done with the previous work was not good enough to say that there is lithium-6. Actually, we do not detect any lithium-6 with these observations. But so for these stars, I needed a lot of observing time. Like each star, I need to observe like at least 5 hours with the largest telescope at the time. That was the case, 10 meters. So I need to be at observing 5, 6, or more hours. But I have some little gaps that I could observe bright stars. And in these little gaps, or just at the beginning of the night, because at the beginning of the night, the sky was too bright to observe these targets related to the primordial lithium. So I say, okay, I'm not gonna waste this time at the twilight. I'm gonna observe some solar flame candidate. And this is how this project started. And so I passed the data to an undergraduate student in Australia, and indeed we found the second star very similar to the sun. At that time, it attracted some attention from the media because it was just the second time that a star close to the sun in physical parameters was found. However, there was a problem that when we look at the chemical composition of this star, it was including that the lithium abundance was too high. These lithium abundance are in log scale, so it was around 0.5 depth higher. That means that it was more or less a factor of 3 higher in the linear scale. So this star, they were similar to the sun, but the lithium abundance was much higher than the sun. Okay, we said we need to keep looking at these solar flames.
Why do we care? Lithium is so little anyway, right? I mean, why is this so important? Why can't we have another solar system just like our own, but except that Earth, instead of having so little lithium, it has more lithium? Maybe humanity or whatever, those people, they will have easier access to lithium batteries than us. But why is that relevant? Or that reveals something else?
Yes, that reveals something about the physics of stellar interiors. So that's some important implications of stellar astrophysics. Yes.
So the origin in those cases is like expected to come lithium from the primordial cloud that collapsed in the star, or like subdominant processes in the fusion that somehow have a channel for this lithium.
Yeah, it's essentially the thing is that the sun has all the stars destroy lithium. The thing is that in the sun we can see that destruction, and I will explain it. So we keep observing. With these initial results, we got some more projects approved. So in that way, we discovered in our first observing run with this telescope with the McDonald Observatory in Texas, we discovered the third solar twin. And this time, the lithium abundance was very close to the sun. This also attracted a lot of attention of the media. Actually, it's not just, even Nature, they made some highlights saying that, oh, look, this is the first time that a star very, very real close to the sun, not just in physical parameters, but even in lithium abundance that we found. And this is not just because the paper is relevant for the general interest, but it is the journalists need to know that there is a relevant result. So what we did was to write a press release. So we wrote the press release and we sent it to a lot of journalists. So some of those journalists became interested and published some articles. Even a guy in the New York Times, he made a competition. He said, look, this study is so important, it needs a name. It cannot be just a number in a catalog. Okay, so it's the first post on the left. Name these solar twins and win a prize. Even offer a prize. I mean, he was
Not to you. Not to you, though.
I won the prize. Not just me. I mean, me and a student from the US, I think.
Okay.
The competition was, look, you need to not just propose a name, but you need to make a myth. You need to create a story, you know. It's not just that you propose a name oh, it's palace or it's
Yes.
whatever. You need to create a story. So I asked to my collaborator that has, I think his father or something, what he needs how to speak Quechua, the language of the Incas. I asked him, look, try to find a name in Quechua and I will write a myth about it. So he found the name, I wrote the myth, and we won the prize.
You want a prize for naming, not for finding.
And what is the name?
I'm curious about the name, yeah.
Intipa Awashan. Inti means sun in Quechua. So Intipa Awashan, I suppose means something like brother or something like that. And the name of the American student, I don't remember what name, but I think it was related to Greek mythology. Okay, so there were 3 solar twins already known in 2007, and we needed a larger sample to try to ask ourselves if there is anything special about the sun or our solar system. So we keep observing. Some of the motivations were papers by Professor Ben Gustafsson in New Zealand. He wrote about 2-3 decades ago. He wrote these papers. Is the sun a sun like a star? Is the sun special or not? So some of his papers were inspiration for our work. And he still keeps working on this subject. So this is related somehow also to exoplanets, as I will speak in a moment. This is so in exoplanet research, we cannot detect yet analogs of the Earth. They are too small to cause an observational effect, both on radio velocities and on light curves. So it's very hard to detect planets like ours. Planets like Jupiter, we are starting to detect. We know several planets like Jupiter, distant Jupiters, I mean, because Jupiters close to the sun, they are easier to detect. You know, they have a bigger influence. But from the theoretical point of view, Jupiter is important to try to keep the configuration of our solar system. So many of these planetary systems, like I don't know how many planets we have today, must be like 5,000 or something like that. Many of those planets, they do not have the same configuration of our solar system. And maybe a similar configuration is important to try to keep a stable planetary system. Not just Jupiter, Saturn is important as well. From this, not just from Andre Isidoro, but also from other calculations, it seems that we are lucky that we have not just Jupiter, but also Saturn, because planets, they tend to migrate. You see here, planets that are the mass of Jupiter, but very close to the host stars. This is because the planet migrates. We are lucky that, okay, Jupiter tries to keep things in order. Small planets here, big planets on the other side. But it didn't migrate much because Saturn kind of keep Jupiter in place.
And what makes them lose environment to migrate?
It's related to the interaction with the disk.
Okay, but then when the disk has collapsed to minor planets, then there shouldn't that be one.
Yeah, so all this happens, exactly, all this happens very early during the first phases. Actually, the formation of giant planets happens very quickly, much earlier than the formation of the rocky planets. I will speak a bit about that. So we we keep looking at these stars, try to make sense of the sun in our solar system as well. This is related also to try to find these solar twins, is related also to try to find planetary systems with similar habitable zones, because the habitable zones depend essentially on the luminosity of the stars. If the stars have a similar luminosity, then you will have a similar habitable zone with similar equilibrium temperatures on the planet. So please. Okay, so we use high resolution spectroscopy. We are happy that we have some equations that make the things much more simple. Everything is put into models, and then what we measure essentially, there are two ways to do this. We either study the line profile, so we compute the emerging flux, the surface of the star, or we measure the total absorption line. That is, the measurement is called the equivalent weight. That is this W over here. And this W is related to the abundance, A here. So the observable is the absorption line. How much absorption we have in each absorption line. And that is translated into chemical abundance. And so we found that related to physical properties, we have many stars with properties similar to the sun, similar air, luminosity, and global metallicity. But there are also other important properties to study, like the magnetic activity of the star, and also the rotation of the star and the detailed chemical composition. And so for the first time, we showed here in this study that the sun is normal in its magnetic activity. The chromospheric activity of the sun is in the vertical axis, and on the horizontal axis, we have the age of the star. And we can see that the sun nicely fits with other stars. So the magnetic activity is much higher when the star is young.
So in the plot here, the stars that you are putting are like already pre-selected to be kind of similar to the sun, like the formation type. Okay, so it's already within sun-like kind of.
Yes, yes. And here is the previous value for the sun is shown by the horizontal red line. So the sun was thought to be much active, but the problem is that the observations were done with another instrument. So there was some systematics, because usually we do not observe the sun with the same telescope that we use to observe the star. But in our project, keep consistency, we observe the sun with the same telescope, with the same spectrometer. The trick is to observe asteroids. So we observe the reflected light. We use asteroid like a mirror, and then in this way we can observe the sun at night. The activity cycle is also that we have been studying. The sun passes through activity cycles every 11 years, more or less. When the sun is more spotted, it increases the number of sunspots, and then it decreases, so the sun has almost no spot. Currently, the sun is at the maximum. So this is something that has been studied in the literature, but just for a few stars, so like 2 or 3 stars similar to the sun. We still do not have a statistical study of a large sample of stars similar to the sun to see if other stars also have a similar activity cycle. This is some ongoing study in our group. Rotation can be determined through sunspots in the sun. In other stars is much harder because we cannot see the surface of the star. So we need to observe another indicators like global variations in photometry, for example, variation in the brightness of the star. The problem is that when, as I said, the stars are very magnetically active when they are young. When they evolve, the magnetic activity decreases a lot. So it's very hard to see variations in the stellar light when the stars are above the solar age, about 5 years or so. It's very hard to do these measurements. And this rotation is important for a field called gyrochronology, because the stars lose angular momentum, and the rotation period increases with time. So if you could measure the rotation periods of a star, in principle, you can tell the age, because you know how much angular momentum has been lost, and then you can tell, okay, this star has many gigayears or so. So this was the classical approach. However, about a decade ago, there was a paper published in Nature saying that, look, actually, maybe the sun, star like the sun will not keep increasing the rotation period. Maybe the sun is at the transition phase right now, and somehow it may keep their carbon rotation period for the future. So this is something that has been discussed a lot in the literature. We have been using our solar twins to show that, according to our results, it seems that indeed the sun will continue to slow down in the future, but this is some ongoing work as well. We are getting new data. Yes.
How to measure age?
The age is measured to the evolution of the stellar properties of the star. When the star
Magnetic properties.
temperature and luminosity mainly, because of the nuclear reactions in the star, the temperature will start to increase very slowly during the main sequence of the star, and also the luminosity. So if you see that the star has a larger luminosity and a higher temperature, then you can see that maybe the star is a bit older. It's essentially a comparison between some observables and some prediction from stellar models on the evolution of temperature.
Luminosity is fully affected by metallicity.
Metallicity impacts a lot. So you need the three: temperature, luminosity, and metallicity. Okay. The issue about the chemical composition of the sun has been discussed a lot since the first determination by Cecilia Bain. She was the first person to determine the chemical composition of the sun, of the stars, including for the sun. And since then, many people have been asking if the solar composition is special or not. And the previous answer from previous work is that the sun seemed typical, the sun seemed normal in chemical composition. And indeed, depending on the size of your error bar, the size could be seems normal, just a regular star. So in order to really see if the star is normal or not, we use solar twins, because the solar twins, you can see here the spectrum of the solar twin, because by definition, the temperature, luminosity, and metallicity of the star, they are very similar to the sun. Therefore, the stellar spectrum is also going to be very similar to the sun. Here at the bottom, we show solar spectrum taken at the same night using through Astro. So with this data of stars, the stars are so similar to the sun that then many uncertainties in the balances are cancelled out if you do a differential analysis line by line. That is very time consuming to do this, but it is worth, because then you can see very, very minor variations in the absorption lines. Maybe here you cannot see, but there is a very small variation of 2, 3, 5% in the line profiles. And you can only detect this when the stars are very similar. To do this differential approach. So back in 2009, I determined the relative composition that is in the vertical axis, where is shown the difference in the chemical composition of the sun minus the average of these 11 solar twins that were observed. Surprisingly, the sun had a different chemical abundance compared to solar twins. We were expecting that all these data points will oscillate here near 0. But it didn't happen. So the sun has a different chemical composition.
So how many twins are you talking about here? The error bars here is just the sample variance of
Yes,
twins.
yes, it's just the standard deviation between the.
So how many twins are in this case?
In this case, just 11.
11 twins.
Yes, but we have repeated this experiment twice, later with 78. So it's the similar result, and lately, just a master student defended a few weeks ago with a bigger sample, was near 100 solar twins, and it was a completely automatic method. She used machine learning to get the chemical balance, and she got similar results. Yes.
The only thing that I would fear there is that suppose that for the selection function of these solar twins somehow, once that you make that sample, the PDF is somehow skewed towards, let's say, a slightly older or
Yes.
maybe younger things that they're like.
Or brighter.
Good point. We also take that into account. We take into account the age of the star, and we do both analysis, correcting for effects of the stellar age, without corrections. And in both cases, we find that the sun is unusual. And this was the eureka moment. When we plot these abundance anomalies as a function of the condensation temperature of the elements, then we found some order. Yes.
Are you using only for relative fluxes, or you have a breakdown?
So it's just the equivalent widths are measured, yes, with relative fluxes, and also in the machine learning approach, we also use relative fluxes. It's very hard to do an absolute calibration. We could do it, but for this kind of precision, is not good enough. So we have to use the relative absorptions.
The reddening.
So this is because the line profile is so the Wheeler high maximum of the line is of the order of 0.1 angstrom. So in this scale, the reddening effect is the differential reddening effect is essentially 0, because reddening is most in a large wavelength scale. So it absorbs a lot more in the blue and much less in the red. But if I compute the differential effect of just 0.1 angstrom, it's essentially 0. Must be 10 to minus, I don't know, 10 to minus 4, something really, really small. But that doesn't matter a lot. That doesn't matter because the stars are nearby. So they are not affected by dust in the solar neighborhood. All these stars are bright, so all those are very close.
Even the 70 ones that your student just used.
There are a few that are the limit. From these 100, maybe 5 are sort of at the limit of this. So the sun is, fortunately, the sun is in something that is called the bubble. The sun is here. It's not a bubble, but the sun is a region of low gravity. And this region is a radius of about 75 parsecs or something. And almost all the stars, except a few like 5 or so, that are very close to this limit. But the rest is inside the limit. So this, the dust condensation temperature is the temperature of the elements in the protosolar nebula. It's related at how the elements condensate, and related to the temperature distribution in the solar nebula. So here at 0, we have the sun, and the temperatures are higher, closer to the sun. When you get farther away from the sun, then the temperature decreases a lot. So like very close to the sun in the protosolar nebula, you couldn't condense water ice, for example, because the temperature was so hot, like 1,000, 2,000 Kelvin. So it's impossible to condense ices. But if you go farther away, like at the distance of Jupiter or so, even a little bit farther away than Mars, then you can condense ices. So that way, our planet got is iron, is rocky material, silicate. It was easier in this region, because in this region, the temperature condensation of those elements are compatible with the temperature of the protosolar nebula, more or less at the 1 astronomical unit, so where the Earth is located. So it was easier to form metals, and it was easier to form rocky material. But farther away, you can form both. At the distance of Jupiter, for example, you can form both. You can form metals, you can form silicates, and also you can form ices. So the planet formation essentially of the giant planets, you need first to form a big rocky core, like 10 Earth masses or so. And then after you have this big core, you can attract a gaseous envelope. And then you build a gaseous planet. But here in this region, you don't have much volatile elements because the temperature condensation was so high. And then in this region, you only form rocky and metals. So this is why we have this difference between the inner solar system, where we can see more rocky material, and the outer solar system, where you can see more ices, more gas, besides the rocks and the metals.
You can ask a very naive question. So this curve should go down because the sun does not have metals, right? This is my question. Why in the sun, the composition of the sun is so different from the Earth? Very naive.
No, the composition of the sun is almost like the Earth. The difference is quite small here, because this difference is just like of the order of 0.4, of the order of 0.08. This means only 10% or 20% more. Just in the more refractory metals, but that is just on the convection zone of the sun. That in radius it looks large, like 23% something, but in the in mass units, it's actually quite small. It's like 2% or so. So all the rest of the sun is has so the sun, according to our hypothesis, is a bit more metal rich on the inside than in the convective zone.
So there's a core of the sun that has metals, like iron.
Yes, the whole sun has metals. It's just a bit different, a bit lower in the convection zone. So it's just like 10%, 20% lower in the convection zone, relative to other solar twins. So, but the sun has a lot of metal. So, in a log scale, the abundance of iron is 7.5 more or less. So it's compared to hydrogen, that in log scale has abundance of 12. Oxygen is 8.7 more or less in this log scale. So the sun has metals. Is what we are seeing here is just that the sun has a bit less metals than other solar twins, and that may be because of the formation of the rocky material that sequester these dust and metals, and then in the late phases of the gas accretion of the sun, that gas that was accreted into the more external part of the sun, that was a bit poor in more refractory metals.
So in this metal, how have they been removed? Just by winds, pressure?
No, the metals are removed by condensation. They condense out in dust.
They stay out.
Exactly. They stay out. They try to they grow. They grow from just 110, 100 nanometers to where we are now today, by different scales of aggregation. On the other side, if you get the Earth and you put it on the convective zone of the sun, then you will increase the metals, the star. So according to some observations, that some stars seem to have much more metals than they should do. According to our explanation, is because those stars have hidden some planets. Yes.
So then, just to clarify, because I don't know if I got the picture right. In the solar system, you had that by some mechanism, you formed a Jupiter planet that didn't allow interior gases to be accreted. You formed other planets in the interior zone, like the Earth, which stayed there and didn't fall within the sun. And in the other counterparts, those planets were not kept in that region because the Jupiter formation occurred like closer, and those metals that are accreted, which enhance the metallicity that you observe. Or is that picture kind of right, or
Okay, so the all giant planets tend to migrate. The good thing about Jupiter is that it makes it more difficult for the giant planets for the other giant planets to migrate inwards. Otherwise, we wouldn't be here because that will alter the orbits of the inner planets, and then it may cause collisions or just ejections from our solar system. So first, probably from Jupiter. Then just about at the same time, but a bit later, for Saturn. And Saturn sort of didn't allow Jupiter to migrate much inwards, kind of push it in, trying to keep him more stable. And then Jupiter didn't allow much migration of the other planets, Uranus and Neptune. Okay, because those small planets also could migrate inward, and then it will be a lot of trouble here. So this time scale is of the order of 10 million years, more or less. While the formation of the rocky planets, the time scale is much longer. You need a lot of time to have all these different scales of aggregation. You have to start with just grains, and then you coagulate those grains, keep accreting it, for people call it pebbles, and then you keep growing this. And so this has a time scale to get into the current planet of the order of 100 million years.
So then it's like, once that you create the Jupiter and Saturn, that have that dynamics, everything kind of goes in place. Like there's a reasonable planet. The only question now is like, why in our solar system there's the formation of Jupiter and Saturn occurred? That it seems that in the others didn't happen because of the metal enrichment. No, that's a bit.
It happens, but because I mean, there are many simulations that show that you could create a variety of different planetary systems. So in some cases, we could end up with a planetary system similar to ours. But according to the simulations, like you simulate hundreds of thousands of planetary systems, the simulations that end up with a configuration similar to our solar system, there are very few. The simulations maybe end up with a planetary system similar to ours. Also, in some simulations, actually, some giant planets manage to migrate inwards. So, I mean, we are just one of the outcomes of planet formation.
Exactly. And the heavy metals that are responsible for the rocky planets, are they consistent with just nuclear reaction in the sun, or you need something else, like, I don't know, intrastar merger or something more exotic?
So that's a galactic chemical evolution. The galactic chemical evolution models currently they can predict qualitatively the behavior, but quantitatively they are not perfect. So the amount of iron that is produced inside the stars, they have to tweak. I mean, this supernova produce how much iron, this massive star is going to produce that iron, that white dwarf merger will produce that much iron. So qualitatively it's okay, but we cannot say just from first principles, look, you have the correct prediction for all the periodic table. That is not currently possible. Just because some of the ingredients, we don't know exactly how much iron or whatever is produced by the supernova explosions. And we have a good idea, but it's far from perfect.
Yeah, and there are many uncertainties to tweak.
Exactly. Yeah, we were discussing that with my students yesterday. They told me, "Oh, why are so many models comparing with observable data of the evolution of oxygen, for example?" Because those are the different possibilities. Those different models are different possibilities of different production of metals. Okay, so that's the idea that a bit of the metals were used to form the planetary material in the solar system. And because of that paper, we said, oh, look, the next step is to try to find planets around these solar rings, because we need to compare the different planetary configurations in the solar rings and in the sun, in order to see if our solar system is typical or not. So we got a lot of observing time when Brazil was considered as an ISO member. And the first planet that we found was a planet very similar to the sun around a solar ring. So we have here the radial velocity curve, and we see that the planet parameters are very similar. Like the mass, the most likely probable mass was around 1 Jupiter mass. Also, the orbit of the planet was more or less circular, was a bit eccentric, 0.14. Semi-major axis, 4.7, very similar to our solar system. Jupiter is at 5.2 astronomical units. So it was really a twin of Jupiter. And this attracted a lot of media attention as well. Oh, and another important aspect is the stellar age. This star has an age that is close to the age of the sun. And in the case of the Earth, we see that we need a lot of time to form a complex life. So people speculated about maybe in this planetary system, if there is a rocky planet, maybe the time is long enough to form a complex life. So this is why it attracted a lot of attention, both here in Brazil and also in other countries. I think we have to,
Yeah, 5 minutes.
Okay, so we have been doing some other studies that is somehow related to planets. And so, for example, we studied the chemical element thorium. Thorium, you know, is a radioactive element. So currently, inside our planet, the chemical element that is providing more energy for tectonic activity and all this activity that we observe in the Earth is thorium. Because the decay time is very, very long. Okay. Other elements like uranium, they contributed a lot in the past, but now it's going down. But currently, thorium is dominant. So we say, okay, by studying thorium in other solar twins, we could see if they have, they are equally capable of having this sort of energy as the sun or not. And the result is showing there. We can see that the other stars actually have a bit more thorium than the sun. Most of the stars have a bit more thorium than the sun. That means that if they form some rocky planets, they will have this source of energy as we do in a bit, even a bit more than.
So that's the Earth here, meaning that if you have another solar system that has more thorium, then I don't know what the scale is in the horizontal heat flow there.
It's like
So it's a log scale.
Yes. For
So-
thorium, it's a log scale.
So if you have 2 times more thorium, then you would generate a huge amount of heat. That's too much then, right? So the habitable zone is actually more far away than what you would assume otherwise, right?
Yeah, so these stars, it's not twice because the log of 2 is 0.3, but it's like 50% more. So yes,
50 or 15?
50. 50% more. So it's a lot more thorium, 25%, 50% more thorium. It's a lot more thorium. I haven't seen any calculations that use more thorium in the planet formation models. That could be something interesting to test. Put more energy. It's not just these radioactive elements that have contributed with the heat. It's also that the residual heat from the formation of the planet itself, it also contributes with a good amount of energy. Okay. Oh, just to say that it's very hard to detect an Earth twin. It's because the signal is very small, just 10 centimeters per second, and also because the stellar noise is very high, of the order of 1 meter per second. That's something that one of my students is trying to study a bit, but it's really very hard. I just want to, I will pull out the lithium. So just this lithium here shows that the difference in lithium was just an effect of the age. Now we understand, and we can compare with models, but at the time we didn't know. So it's just the destruction of lithium inside the star. That's also a lot of tension. Just looking at this node here, that other groups have been also working on different aspects of these solar twins. I found these two works very interesting because the chemical abundance are so good, they could try to make a more precise models of the evolution of the chemical abundances these stars. So Paulo and Jorge in Chile is trying to use some techniques from evolutionary biology to try to see if they follow some similar behavior. And this work is very fascinating, using the solar twin, because these stars are so similar that you can get more precise measurements of the center of the line of absorption. And then you can try to see if the same physics that we should use here could be used in elsewhere. And so they make a very strict test of the variation of the fine structure constant. For example, using this measurement on solar twins in pair of lines solar twins. Okay, that's it. Obrigado.
So what you started your talk with the Drake equation. I remember one of the most my earliest memories of thinking about this stuff was Carl Sagan talking about the Drake equation. I don't know if Jorge maybe remembers this. We are but so do you dare to go back to this? And because I remember having seeing several versions of this. I mean, there are many assumptions that you can have in there, but you're very focused on things which look very much like our sun, our Earth. So do you dare to go back to the Drake equation and make something like this for, let's figure out how many Earth-like planets we have in the Milky Way that can have life like our own kind of life?
Yeah.
Did you ever attempt this?
It's very little. It's really very little. So there is a question. The first is the star formation rate. So how many stars you can form. Then the second parameter is the fraction of stars with planets. Now, thanks to Kepler, the Kepler telescope, we know that more or less each star has, in average, at least one planet. The third parameter is more difficult. So how many of those planets could be more similar to the Earth? We are getting close to that, not directly, but indirectly through if we say that, okay, we cannot detect Earth yet, but if we say that planetary systems with a similar giant planet configuration could be similar to our solar system, then maybe we could try to estimate that fraction. That fraction is very small. From our own survey of planets of the solar twin, if I remember correctly, the current fraction is around 3%. So from all planetary systems, the planetary system similar to ours is probably just a small fraction. So the field parameter we could know.
It's still a huge number. I mean,
It's a huge number.
it's a small percentage, but it's still a
You see
huge
that
number.
it start to get complicated as we
Yes.
go towards the
Right.
back. So the next is the fraction with life. As I said, the basic life is fine. Maybe it's complex in the universe, so bacteria, but more complex life like ours, it maybe it's a matter of time. So good news is that there is this project called the Habitable Worlds Observatory by NASA. And they're going to observe like 100 stars or so to try to see which one of them could be habitable. So in the future, we may have some better estimate of this fraction, but in principle, it should be close to 1. I mean, anywhere you have a good Earth-like planet, maybe you will develop life at some point. The next one, intelligent life. So intelligent life is a problem because, I mean, do we have intelligent on our planet? At what point, right? And you need a lot of time. I mean, the more complex life structures, you need to wait 4 gigayears or so to develop, at least on our planet. So that's something uncertain. The next one, the fraction that develop civilization. So it means a bit more time and that you actually develop a civilization. I mean, you could talk about intelligence, different animals have different levels of intelligence, but from there to go to a civilization is another problem. And finally, that's the most uncertain, the last one, the lifetime of a civilization. For how long are we gonna be here, right? It's just a few more thousand years. I mean, right now it's a bit chaotic. Right?
Timely question.
So it's hard. It's hard as you go towards the right of the. Maybe this is why we put the parameters in this order. I have a quick question.
Oh, you're.
slower. So I noticed that you don't use Gaia data. We thought that Gaia would give you billions of stars or something. That's
Yeah, so yes, currently we are using Gaia data, but when the project started, we have to use the Parcos. Yes, because Gaia was not ready yet. It appeared only like a decade later.
But now you're using Gaia too.
Now we're using Gaia data.
And at the moment, it's like 100 in.
Now with Gaia, we have another 100 more. This is just in the southern hemisphere. The northern hemisphere must be like double the number.
And with Jupiter, just 1 or 2.
Jupiter, there are a few Jupiters now in the literature. I mean, not strictly Jupiters, but by the way,
In twins.
this is a prize that I got the mythology Bible. So here are some estimates from different surveys. Jupiter life is all of them show that is included our own survey. It's like 3-4%. It's really small fraction.
Less than 2. Have a very short break, and then we resume in 8 minutes.